Anyone know? George Biddell Airy. He was I think he held a record for being the Astronomer Royal for 46 years. I didn't check that, but it must be. I can't think of any other Astronomer Royal who lasted for 46 years. And he was born in, I think it's Northumberland, Alnwick. He went to a Colchester school and then to Trinity College. He had a sight problem, a problem with his eyes, seeing various colours, seeing light. So he got interested in the physics and light and optics. That was his first thing. Anyway, he later became the director of Cambridge Observatory, and he was 5 times the president of the Royal Society. I mean, that takes some beating, doesn't it? As Astronomer Royal, he did a lot of good down at Greenwich. A lot of the equipment was old, out of date. So he developed quite a lot of new instruments, got people to do more observations, particularly of the sun, the solar system, did spectroscopic observations, and then also started off some work on photography. Outside of astronomy, he was involved in other things, actually, quite surprised at reading about this, in laying the transatlantic cables using the SS Great Eastern. I expect you've heard there was the SS Great Western, wasn't there, and the SS Great Britain. This was the SS Great Eastern. And also, I don't understand this one, but he actually had something to do with the chimes of Big Ben. That seems a strange thing. Anyway, all that lot seems good. He did a lot of good, but there's one thing actually he was a bit of a pest with. He actually, I wouldn't say arguing, but he actually did not like the work being done by one of my fellow countrymen, the Cornishman, John Couch Adams. John Couch Adams actually made an estimation of where the planet Neptune might be. And he passed all his information on to Airy, who he thought Airy might encourage other astronomers to look. But Airy was not interested at all. And after a short time, the information got over to France, to Leverrier, and he was more interested in it. And it was through Leverrier and a German astronomer, Galilei, that Neptune was discovered. So if actually Airy had actually taken an interest with John Couch Adams a few weeks before, I'm sure he would have discovered Neptune. There was one person in England who actually had to go, an astronomer at Cambridge called Challis. And Challis did look, and he said, I have found Neptune. He actually did a plan. He said, but I've got to check tomorrow night and perhaps the night after, to see if it's moving amongst the stars. So for some reason or other, he didn't get around to looking at that. And if he did, perhaps the very next night, perhaps the night after, he might have been the discoverer of Neptune. So that was a shame he missed that, actually. So John Couch Adams could have been the discoverer, or Challis could have been the discoverer. So that was the only really, what should we say, spanner in the works for Airy. He seemed to be a very good Astronomer Royal over his 46 years. It's worth actually reading some of his work. Actually, there were other things he did. It's worth reading about them on Google. Okay, then, that's my anniversary for the day, 27th of July, 1801, the birth of George Biddell Airy.
Right, very interesting.
Okay.
Very interesting.
Thank you.
That's really good, that, yep.
Did he come up with Airy disc?
The Airy disc, yes, you got it. Yeah. Yes, there's quite a lot of things actually I've left out. I suppose someone could have talked for an hour on Airy. I will ring up Bob when I get home tonight or tomorrow morning and tell him about it and see how he's getting on with this wretched Windows 10, which I'm having to put up with. I had to go and get my computer sorted out. And of course, without asking me, they stuck in Windows 10. I'm getting used to it though, but there's certain things I can't find. I haven't been able to find some of the Windows thing, the PowerPoint that seems to have disappeared, and Windows Word, and just seems to have disappeared completely. Never mind, that's another story. Okay, thanks a lot.
So, has anybody got any questions for Eddie?
Any questions? Or have they gone to sleep?
Hope not.
Not yet.
No pressure, Roy.
But thanks, yeah. Okay.
But as I said, I might have to leave early. The weather is starting to rain now, and I've got nearly 50 miles to go down the motorway, and I want to do that before the road gets flooded again. It was terrible coming up.
Yeah, I was out today and there was almost a river running down the local road.
Yes, 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 yes. And you go along at 40 miles an hour on the motorway in the rain, spray coming up. People are still zooming past at 70 and 80.
Yeah.
Oh, safe journey home.
Thank you. Lorries are still doing 70 and 80 some of them as well. Oh, not a safe place to be. As I said, I saw a caravan spun across the road with the Land Rover towing it, and then a great big lorry ended up in the ditch as well.
Oh dear.
Anyway, okay, thanks.
Yeah.
I've had my say. I rest my case.
Yeah. Thank you. Bye-bye.
Yeah.
Thank you. Bye.
So shall I? No. We need to set up the screen share. Just give us a second. Yeah. According to my phone, that should be what we hope to see.
Good.
Just take this computer, just takes a wee second or two to warm up. Okay. And I'm recording this, so I'm just going to cut it down to a single thumbnail. Better make it me. So I don't particularly like doing it, but I'm just going to mute everybody, but you can come in if you want. So is that muted, everybody? Seems to have done.
Roy, it's Alan Henderson here. My wife's interested in geology, but believe it or not, she's on another Zoom meeting, so she'll join us later if that's okay.
This isn't.
Yeah, I had unmuted myself, so I'll do it again.
Right, so I'll unmute myself.
Okay, and now I've disappeared. That's it. Right, Alan's showing up instead of me. Can you hear me speaking okay?
Yes.
Oh, okay.
Yes.
That's good.
Yeah,
Right.
great.
So, when I retired about 10 years ago now, I did what an awful lot of retired folk do. I got a bit bored and eventually started going out and walking out in the countryside. And as you do after a while, you've got plenty of time to think. So I was looking around and thinking, oh, I wonder why the mountains look like this and the hills look like this. And when I got home, all I had to do, obviously, was just look it up on Google and find out stuff. But what I'd like you to do for the first part of this talk, if you can, is imagine you were back, well, it's not off 2,000 years ago, but imagine it was quite a while ago. Hang on a sec, I just lost my notes. Got them back. Try and imagine it's a couple of thousand years ago. You don't really know what's going on. You don't understand what the world's all about. So you want to, you're an interested person, you want to see sort of, you look around, you see hills, you see mountains. And then you think, what else can I see? Well, if I go down to the coast, I can see beaches and I can see some weird looking mountains called volcanoes. So I'm still, let's try this again. I think that's, yeah. Doesn't seem to be muting everybody. I'm not sure what's gonna, anyway, if you could be aware that some people aren't muted, so we can actually hear you. So, as I say, if you're a rich person and you wanted to find out a bit more about the world, you might decide to go up into the mountains and try and find out how they're formed. And on your way up, you might come up to a river glen like this, and if it's in the springtime and you look down in the river, you might notice that some rocks have fallen off the side of the mountain, probably the frost got at them, and the big chunks lying down in the river, they're still quite sharp because they're just fallen off. You've sort of run out of time in sandwiches, so you decide you better go back down to where you were and you walk back down the river, and you notice that actually the bits of rock that you saw earlier that were quite sharp are beginning to have their edges rounded off them as they tumble down the river. The further down you go, the more rounded the pebbles become. And if you go even further down, yet again, pebbles are all getting mixed up. There's different types of rock in there, but they're all more and more rounded, and eventually they're going to become, in fact, you can see some of them here are actually even spheres. And if you go right down to the coast, you can get to this sort of situation where the pebbles have completely disappeared and it's all just tiny little bits of chipped rock or perhaps sand. If you come somewhere else, you see something like this. You're at a sandy beach. So you look at the sand, you look at the boulders you saw up in the mountains. Boulders get smaller and smaller as they roll all the way down. So if you're the earliest geologist on the planet, you might decide that perhaps what happens is the mountains get worn down by the weather, and then all this washes down into the sea, and somehow or another, especially looking at this, if you look at this rock, this looks like it's just huge, great layers of sand. So your sort of major theory is that everything gets washed down into the sea, somehow or another it gets converted into rock. And that was really the first principle of geology, and it was called Neptunism. However, there's a bit of a problem with that, in that if it was just mountains rolling down, or rocks rolling down off the mountain, you look at this and you think, well, hang on a minute, why should you have different coloured pebbles rock rolling down, and why is there such a clear definition between the layers of sand here and the different colours? Perhaps it's not sand, but again, you know, so where did all this come from? Or you look at this, and this is another type of rock. And again, this looks much more like it was just the stones at the bottom of the river that we saw earlier on, but somehow or another, they've got joined together. And actually it's, I don't know what it is, a conglomerate we call this. But anyhow, somehow or another, this doesn't really tie in terribly well with the idea of all this stuff being washed down to the bottom of the sea and being compressed into a rock. So let's have a wee look now again, trying to pretend that we don't know any geology at all, and we're looking at it from a fresh angle, because the early thinkers, they didn't know anything else. They didn't have the machinery we've got, the technology we've got. They just had to look at stuff and try and figure it through. So as you probably worked out, that was mostly just me talking. I'm going to have to start reading some stuff now, so apologies for the reading, but it's the only way I can do this. First of all, we come to James Hutton. He was born into a well-to-do family in Edinburgh on the 3rd of June in 1726. His father was a wealthy merchant who was also the Edinburgh city treasurer. Hutton's father died in 1729 when he was only 3 years old. He was educated at the High School of Edinburgh, where he was particularly interested in maths and chemistry. And then when he was 14, he attended the University of Edinburgh as a student of humanity, studying the classics. 14, by the way, was the normal age to go to university back in those days. He was apprenticed to a lawyer when he was 17, but took more interest in chemical experiments than legal work. At the age of 18, he became a physician's assistant and attended lectures in medicine, also at the University of Edinburgh. After 3 years, he went to the University of Paris to continue his studies, taking the degree of Doctor of Medicine at Leiden University in 1749, with a thesis on blood circulation. After his degree, Hutton went to London, and then in the mid-1750, he returned to Edinburgh and resumed his chemical experiments with his close friend, James Davy. He was therefore a very well-travelled and a highly educated individual. Unfortunately, like Rabbi Burns, he was also a bit of a Jack the Lad. And after one unfortunate pregnancy too many, he was advised to leave Edinburgh society urgently. So he became a gentleman farmer on the family estate down in Berwickshire. Once he moved there, he set about making improvements, introducing farming practices from other parts of Britain, and experimenting with plant and animal husbandry. He recorded his ideas and innovations in an unpublished treatise called the elements of agriculture. This developed his interest in meteorology and geology. In 1753, he wrote that he'd become very fond of studying the surface of the earth and was looking with anxious curiosity into every pit or ditch or bed of a river that fell in my way. Clearing and draining the farm provided ample opportunities to look at things. The mathematician John Playfair described Hutton as having noticed that a vast proportion of the present rocks are composed of materials afforded by the destruction of bodies, animal, vegetable and mineral of more ancient formation. His theoretical ideas began to come together in 1760. While his farming activities continued, in 1764 he went on a geological tour of the north of Scotland with George Maxwell Clark, an ancestor of the famous James Clerk Maxwell. In 1785 at Glen Tilt in the Cairngorms, Hutt found granite penetrating metamorphic schists in a way which indicated that the granite had become molten at the time of intrusion. It's not actually terribly clear in this photo, unfortunately, but this stone here is pink granite, and these are all grey rocks at the side. I couldn't get a clearer picture to come up, sorry about that. This demonstrated to him that the granite formed from the cooling of molten rock rather than it precipitating out of water, as the Neptunists at the time believed. And therefore, the granite must be younger than the schists on either side of it. Hutton then started searching for further evidence that rocks had not simply been laid down on top of previous older layers of rock. He went on to find similar penetration of volcanic rock through sedimentary rocks in Edinburgh, at Salisbury Crags, adjoining Arthur's Seat. In this area of the crags, Janice, sorry.
Excuse me. Are we supposed to be seeing something? Because all I can see is yourself. Are we supposed to be seeing a picture? When you said about these stones or something.
Are you not getting the slides up?
No, how do I get them?
I can see.
I'm not sure what's going on. Is everybody else? Sorry.
Yeah, I'm getting the slides all right.
Yeah, I'll get
Yeah.
Yeah. Oh, how do I get them?
Get the
Oh,
slides.
I've
It's
got the
coming up.
slides.
My phone's connected in the way everybody else should be.
Oh, that's it.
Yeah,
I had
okay,
to
just-
switch to screen share. It's just when you started on about stones, and I thought I'm not seeing anything.
All right.
Sorry. I'll unmute myself now. Thank you.
Right, so, where are we? So Hutton found other examples of this in both Galloway in 1786 and on the Isle of Arran in 1787. So I think, Neville, you're still not unmuted. I'm going to try and mute everybody again. Yeah, Hutton's idea was that mountains were built up and then eroded away, then built up and eroded away. So it's possible for there sometimes to be no record of the different layers of rock that once existed. This is called an unconformity. So you can see that on the right-hand slide. This is an unconformity in Arran. The almost vertical rocks in the foreground are, just using the correct term here, Dalradian schists, and they're about 520 million years old. The rocks in the background, going across here, are Kinniswood group, and they're only about 360 million years old. So that wee gap there of about an inch represents a missing chunk in the rock record of about 160 million years. This is the wonderful Sicker Point, which I've been to about 3 times. It's just gorgeous. In the spring of 1788, Hutton set off with John Playfair to the Berkshire coast and found more examples of this sequence in the valleys of the Tour and Peasburn near Coburn's Path. They then took a boat trip from Dunglass Burn east along the coast with the geologist Sir James Hall of Dunglass. They found the sequence in the cliff below St Helens, then just to the east of Sicker Point found what Hutton called a beautiful picture of this junction washed bare by the sea. Somebody's making a racket. Playfair later commented about the experience. The mind seems to be by looking so far into the abyss of time. Continuing along the coast, they made more discoveries, including sections of the vertical beds showing strong ripple marks which gave Hutton great satisfaction as a confirmation of his supposition.
Okay, Cat.
Laid horizontally in the water. Hutton reasoned that there must have been innumerable cycles, each involving deposition on the seabed, uplift with tilting and erosion, then undersea again for further layers to be deposited. On the belief that this was due to the same geological forces operating in the past, at the very slow geological forces seen operating in the present day, the thicknesses of exposed rock layers imply to him truly enormous stretches of time. Because of this, Hutton's credited with originating the concept of deep time. Again, pretty good photo, but if you can see here, this is sandstone that was laid on the bottom of the seabed. This is sandstone that was laid on the bottom of the seabed, but this is vertical and that's horizontal. So what Hutton's saying is that everything starts off like that, but then something's causing things to move and get bashed about, and eventually something goes up like that, and then it sinks down under the sea, and then more sand falls down on top of it, and it forms into sandstone. So, but his main point, and the main point I'm trying to make here, is that obviously that's going to take an awful long time. And again, remember, officially, when he was writing all this and thinking about all this, the world had been invented by God about 3,500 years ago. And he really couldn't understand how something like that could happen in 3,500 years. So the next famous Scottish geologist is John Playfair. He was born at Benvie, slightly to the west of Dundee. He was educated, let's see if I can, I'm trying to make this just a wee single picture again. For some reason, whenever I do that, I get eddies. Eddie, can you mute yourself? No, well, never mind. Okay, I'll just leave that there. Oh, thanks, Eddie. Right, so this, hopefully this should just become me now.
All right, has he done it now? Because it was the only one that wasn't unmuted.
Ah, well, now you're now in the top.
Yeah.
So if you can mute yourself again.
Yeah, I will do, but he was the only one that wasn't
No,
unmuted.
if you can mute yourself, then I can start recording again, thanks. I don't know what's going on. Okay. Hey, John Playfair was also educated at home until the age of 14, when he entered the University of St Andrews to study divinity. He also did further studies at Edinburgh University. In 1773, he was licensed to preach by the Church of Scotland. However, Playfair chose to continue his studies in maths and physics. And in 1782, he resigned his charge to become a private tutor to the gentry. By this arrangement, Playfair regularly visited Edinburgh and went on to cultivate the literary and scientific society for which the city was at the time especially distinguished. Although through Neville Nasquillan, whose acquaintance he'd made in the course of the celebrated Schehallien experience, which we'll talk about later, he also gained access to the scientific circles in London. In 1802, Playfair published his celebrated volume entitled Illustrations of the Huttonian Theory of the Earth. The influence exerted by James Hutton on the development of geography and geology is thought to be largely due to this publication. So Charles Lyell was a Scottish geologist born the year after Hutton died, who demonstrated the power of known natural causes in explaining Earth's history. Principles of Geology, Lyell's first book, was also his most famous, most influential, and most important. First published in 3 volumes between 1830 and 1833, it had established Lyell's credentials as an important geological theorist and propounded the doctrine of uniformitarianism. It was a work of synthesis backed by his own personal observations on his travels. Like Hutton, he was a very well-travelled man as well. The central argument in Principles was that the present is the key to the past, which I stuck up in red. The concept of the Scottish Enlightenment, which David Hume had stated, was all inferences from experience suppose that the future will resemble the past. Geological remains from the distant past can and should be explained by reference to geological processes now in operation, and thus directly observable. Lyell's interpretation of geological change as the steady accumulation of minute changes over enormously long spans of time was a powerful influence on the young Charles Darwin. Lyell asked Robert Fitzroy, the captain of the HMS Beagle, to search for erratic boulders, also more of which later, on the survey voyage of the Beagle. And just before it set out, Fitzroy gave Darwin volume 1 of the first edition of Lyell's Principles. When the Beagle made its first stop ashore at St. Diego in the Cape Verde Islands, Darwin found rock formations which, seen through Lyell's eyes, in his words, gave him a revolutionary insight into the geological history of the islands, an insight he applied throughout his travels. However, sometimes Lyell got it wrong. In Principles of Geology, Lyell proposed that icebergs could be the means of transport for erratics. I mentioned erratics a minute or two ago. As you can see on the photo of that, there's this huge boulder, which is of a completely different rock type than anything else round about it. He thought that during periods of global warming, ice breaks off the poles and floats across submerged continents, carrying debris with it. He thought that once the iceberg melted, it rained down sediments upon the land. Nowadays, we call these rocks glacial erratics, as we can now prove they're actually dropped when glaciers melt. Of course, again, going back to this idea of trying to look at the world the way these people look at it, if you lived in Scotland, you wouldn't be thinking that there had been glaciers around there. That part of the thinking hadn't really been worked through. And similarly, on the right, Lyell believed that the accumulation of these fine angular particles covering much of the world called loess was a deposit settled from mountain floodwater. Again, this idea that everything washed down off mountains. Again, we now know that these formed in desert environments, but Lyell couldn't know that the continents themselves move over the surface of the earth. That said, many of Lyell's mechanisms and processes have stood the test of time. His observational methods and general analytical framework remain in use today as the foundational principles of geology. Lyell's work on volcanoes focused largely on Vesuvius and Etna, both of which he'd earlier studied. His conclusions supported the idea that volcanoes build up over very long periods of time, so-called backed up building, as opposed to the southern upheaval argument that other geologists had. In other words, other geologists at the time thought these would just blast themselves up in huge explosions over a sort of 20 to 30 year period. They didn't really have much knowledge of volcanoes around the world. I mentioned earlier the Schiehallion experiment. John Playfair had been involved in this experiment. It was a project to determine the mean density of the Earth. Founded by a grant from the Royal Society, it was conducted in the summer of 1774 around the Scottish mountain of Schiehallion in Perthshire. The experiment involved measuring the tiny deflection of a pendulum due to the gravitational attraction of a nearby mountain. Schiehallion was considered the ideal location for this, thanks to its isolation and almost symmetrical shape. The experiment had previously been considered, but rejected, by Isaac Newton as a practical demonstration of his theory of gravitation. However, a team of scientists, notably Neville Maskelyne, the Astronomer Royal, was convinced that the effect would be detectable and undertook to conduct the experiment. The deflection angle depended on the relative densities and volumes of the Earth and the mountain. If the density and volume of Schiehallion could be ascertained, then so could the density of the Earth. Once this was known, it would in turn yield approximate values for these for the other planets, their moons and the Sun, previously known only in terms of the relative values. As an additional benefit, the concept of contour lines, devised to simplify the process of surveying and mapping the mountain, later became a standard technique in cartography. Maskelyne came up with a value of 4,500 kilograms per cubic meter, in comparison with the modern accepted figure of 5,515 kilograms per cubic meter. So just by measuring with a pendulum, the density of the Earth had been computed with an error of less than 20%. which I think is pretty astonishing. The shelling experiment was repeated in 1856 by Henry James, who was the Director General of the Ordnance Survey. And this time they used Arthur's Seat in central Edinburgh. With the resources of the Ordnance Survey at his disposal, James extended his topographical survey to a 21-kilometre radius, taking him as far as the borders of Midlothian. He obtained a density of about 5,300 kilograms per cubic metre. This is incredibly close to, as we say, the 5515 that we use or we know nowadays. The modern re-examination of the geophysical data of the Schiehallion experiment was able to take account of factors that the 1774 team couldn't. With the benefit of a 120-kilometre radius digital elevation model, greatly improved knowledge of the geology of Schiehallion, and also a computer, a 2007 report produced a mean Earth density based on those figures of 5,480 kilograms per cubic metre. When compared to the accurate figure, it really does stand as a testament to the accuracy of Maskelyne's measurements, and which was of course learnt during his astronomical observations. We've had a look at how people were looking at rocks and trying to understand how they formed. We'll come back to look at some of the answers for that later. But for now, let's take a wee side trip into the world of fossils. Sadly, nobody Scottish of note appears in the early story, so we'll have to go to the south of England for an interesting historical figure. Mary Anning was an English fossil collector, dealer and paleontologist who became known around the world for important finds she made in Jurassic marine fossil beds in the cliffs along the English Channel at Lyme Regis. Her findings contributed to important changes in scientific thinking about prehistoric life and the history of the Earth. Anning searched for fossils in the area's Blue Lias cliffs, particularly during the winter months when landslides exposed new fossils that had to be collected quickly before they were lost to sea. She nearly died in 1833 during a landslide that killed her dog. The discoveries included the first Ichthyosaur skeleton, the first two almost complete plesiosaur skeletons, and the first pterosaur skeleton located outside Germany, and important fish fossils. Her observations played a key role in the discovery that coprolites, known as dinosaur poo, known as bezoar stones at the time, were actually fossilized, as I said, dinosaur poo. She also discovered that belemnite fossils contain fossilized ink sacs like those of modern squid. And the geologist Henry de la Beche painted Juria Aquitador, or Antiquidor, the first widely circulated pictorial representation of a scene from prehistoric life derived from fossil reconstructions. He based it largely on fossils Mary Anning found, and sold prints of it for her benefit. Mary struggled financially for most of her life. Her family were poor, and her father, a cabinet maker, died when she was only 11. After her death in 1847, her unusual life story attracted increased interest. It's often been claimed that her story was the inspiration for the tongue twister, "She sells seashells on the seashore." There are fossils to be found in Scotland, but most of the ones I've found have just been of small sea-dwelling plants in limestone and local quarries. If you're looking for dinosaur remains, the best you're likely to see are these footprints found in Ancoran Beach on the Isle of Skye. So I don't know if it's terribly clear, but that's a human footprint. And you can actually see the three-toed dinosaur footprint there. There's also some interesting fossilised trees to be seen here in Glasgow. Either visit the original site of Fossil Grove in Victoria Park, or see a removed fossil in the fossil tree trunk in the Kelvin Grove Museum. The trees in Fossil Grove are unusual in that they can still be seen in their original location in the heart of the city. I mentioned earlier that Charles Lyell couldn't know about the continents moving about in the Earth's surface. So I suppose I should give a wee bit more detail about how we came to understand this. It will also be difficult to understand some of the Scottish features we'll be looking at soon, unless you at least appreciate that the continents have moved over time. Since the days of the first maps of the world, it had always seemed a bit odd that the left-hand side of the map looked like it fits snugly against the right-hand side. Things get even more odd when early fossil discoveries showed that the fossils in Scotland were the same species as fossils in Canada, but completely different from species of the same age found in England. It was as if Scotland and Canada used to be joined together, and Scotland used to be separate from England, as some folks seem to now want it to be. Alfred Wegener thought about these sorts of discoveries, and in January 1912, he presented his ideas to the German Geological Society. His hypothesis was that the continents had once formed a single landmass called Pangaea before breaking apart and drifting to the present locations. Wegener was the first to use the phrase continental drift and formally published the hypothesis that the continents had somehow drifted apart. Although he presented much evidence for continental drift, he was unable to provide a convincing explanation for the physical processes that might have caused it. His suggestion was that the continents had been pulled apart by the centrifugal pseudo-force of the Earth's rotation, or perhaps by a small component of astronomical precession. However, these ideas were rejected because calculations showed that the force wouldn't be sufficient. Pretty much, in fact, nobody believed his ideas had any merit at all. However, technology moves on, and we now have a mechanism that proved Wegener to be correct. This animation, which should be coming up in a second or two, there you go. This shows how we think the continents have drifted around over the Earth's surface during the last 250 million years. The bit I like is how India breaks off Africa and then smashes into Asia. Eee, bang, lovely. As the continents drift apart and crash into each other, huge amounts of lava are released to the surface of the Earth. You got stuck there, here it is. To bring this talk back to Scotland, and also to get in some more pretty pictures, here is the columnar basalt you will find on the Scottish island of Staffa. Columnar basalts like this are formed when deep lava flows accumulate over a cold base, then cool and solidify from both the top and the bottom surfaces. As very thick and deep lava cools slowly, cracks form in hexagonal shapes, resulting in what you can see here. And here's the same columnar basalts that you find in the Giant's Causeway in Northern Ireland. The sites on the two slides haven't drifted apart. This feature actually continues underneath the Irish Sea. During the 19th century, Knockencrag became the subject of much debate when geologists noticed that the moin schists at the top of the crag, just north of Ullapool, appear to be older than the Cambrian or Ordovician rocks such as the Durness limestone. That's this one in here, lower down. Disagreements over the processes that could have caused this to occur were referred to at the time as the Highlands Controversy. National Heritage Scotland had built the visitor centre you can see here on the right to explain to the public the work of Ben Peach and John Horn, who spent 1.5 years, think about that, in the Highlands, camped out in the worst of the weather the Highlands could throw at them, surveying and mapping the landscape to provide the clues to resolve the issue. So, what was the issue? Let's see if I can get this drawing to work. Let's do that. So you can see down here, hopefully, that the rock above this line and the rock below this line are actually completely different types of rock, and they're completely different ages. So, and going back to the talk, the results of the mapping proved conclusively to Peach and Horn that the contact was tectonic, that's movement in the plates. The recognition of the Moyne thrust belt in the early 1880s was a milestone in the history of geology, as it was one of the first thrust belts discovered, and where the importance of large-scale horizontal rather than vertical movements became apparent. Detailed mapping of the Moyne thrust belt by the survey continued for another 2 decades, culminating in the classic survey memoir, The Geological Structure of the Northwest Highlands of Scotland, published in 1907. So Peach and Orne, as I say, proved that the rocks on the top had been thrust 20 kilometres from the original position over the older rocks below. So again, I mentioned earlier on, I tried to do the wee thing showing that things have been pushed together and gone like that and then bent over so it's a sicker point. In this case, what happened was that, and again, remember, this is all about 10 kilometres down, it's not happening on the surface. So there's a lot of pressure stopping things. But this time, the movement goes like that. And this got pushed up and on top of the other bit of rock. And as I say, that's all happening about 30 kilometres. So eventually, erosion brings all this up to the surface. And you can now see that sort of shape. So this is why, as I say, it's called a thrust. So let's do a wee bit more thrust talk. Oh no, what's happened here? I think I've got to switch that off first. Let's try this now. It's all right, technical problems. I might have to. Oh, major technical problems. Hey, phew. Everything's back to normal. This is the classic photo of Ayers Rock in the sunset. But what I want you to know is actually the similar rocks in the background called the Olgas that folk don't tend to talk about much. No, I've got this blue line still here. I'm going to take, sorry, I've got to get rid of it. It's all right. Right, back to the talk. Also, it's quite clear if you look at this that the sedimentary layers in the sandstone of Uluru are almost vertical. I've lost control of this, making it go. So if we look at the Olgas, we can see from the close-up at the bottom left that sedimentary layers are horizontal. Both Uluru and the Olgas are part of the same rock formation. So why is one part horizontal and one part vertical? You can see here that both outcrops are actually in the same formation. But the movement of the Earth's tectonic plates meant that over time, the part of the formation at the right-hand side of the slide were forced up more than the part of the formation on the left. It makes this thing, things are moving, things being shoved about. So much so, this bit became horizontal. In the mine thrust, the rocks couldn't bend, so one section was pushed over the top of the stronger continental rocks. Erosion of the surface layers means that some of the formation in the middle of the slide has disappeared completely. And the area generally has been filled in by more sand, covering up the evidence that it's all one rock type. So let's have a wee look at volcanoes now. Excuse me a sec. Most volcanoes are formed when ocean plates are driven under continental plates, although some can form in the middle of oceans over rising magma called a hotspot. The oceanic crust contains dissolved water. As it gets deeper, the rock begins to melt, and the water-infused rock begins to rise towards the surface, as you can see in the animation on the left. As it rises and the pressure decreases, the rock becomes less dense and more liquid, and eventually bursts through the crust as lava. If there's still a lot of water in the lava, these eruptions can become explosive. However, this presentation is based on Scottish geology, and there's no volcanoes currently erupting in Scotland, but there used to be. And here's what a volcano looks like after it's been eroded for 340 million years. And here's what it looked like originally. And this is Loch Soonart in Ardnamurchan near Fort William. Can you see the volcano? No. Me neither, I'm afraid. How about have we look at it from the air? And that's why people create geological maps. I think you can now see the huge cone of the volcano as was. Careful observations on the ground, followed by drilling boreholes to bring samples up from the depths, allows geologists to create the maps that illustrate the origins of the landscape we see today. An even bigger volcano has been eroding here for even longer. Does anyone recognize this? No? It's the Black Cooling Sun Sky. It's now thought that the whole of Skye is really just the remaining stump of a huge volcano that exploded catastrophically about 560 million years ago. This explosion made Krakatoa look like a damp squib. There's evidence that the amount of gas and dust blown into the atmosphere led to an increase in global temperature of 8 degrees centigrade. That's 4 times the increase that were predicted to create huge problems for present-day humans. Driving through Scotland from the south shows fairly dramatic and sudden changes in scenery. It doesn't really look like it from the diagram, but the Highland boundary fault separating the Highlands from the lowlands bends down through the middle of Arran and then onto Northern Ireland. This is why the north of Arran is mountainous and the south flat. It also gives a clue to why, as we saw earlier, Staffa and the Giant's Causeway are made of similar material. This slide again emphasises that Scotland and England were once literally on different continents. As we've seen on earlier slides, what happens when on the large scale when continents collide. Now we're going to have a look and see what happens on a smaller scale. So, again, this was the continent of Florentia. This was the continent of Avalonia. When they eventually bashed into each other, you got the Caledonian Mountains. So, I mean, we call Scotland Caledonia. Caledonians go all the way down there and all the way up through Scandinavia. These are the oldest rocks in Britain, and it's called Lewisian gneiss after the island of Lewis. They were formed when the early continents of Laurentia and Baltica, we saw on the last slide, collided, forming the Caledonian Mountains, all the way down the east coast of Canada and USA. This happened between 3 and 1.5 billion years ago. When the Atlantic Ocean started to form about 200 million years ago, a small chunk broke off and landed up attached to what is now Scotland. And as we saw from continental collisions, this is the sort of stuff that geologists love. Nothing like folded rocks to get excited about. And again, you've got to remember that rocks like this fold under high pressure and deep down under the earth. And the rocks are pretty much like plasticine. So again, try to explain this picture here. Think of it like this, probably things together, pressure coming in on the side, slowly, slowly, in a plasticky way, forms together, and you get a peak here. It's obviously the top of something huge, and we're looking at just the very top of it, and then everything else keeps moving, and it gets tilted over like that, and eventually you get the sort of thing you can see in front of you there. This is the southern uplands. The southern uplands consist mainly of Silurian sedimentary deposits that were dropped in the Iapetus Ocean about from 500 to 400 million years ago. These rocks were pushed up from the seabed into a wedge during the Caledonian mountain building that we just talked about 400 million years ago. Just have a think about it. The whole of these southern uplands are actually just the stuff that got pushed to the side as the main mountain ranges were being formed. This slide shows one of the many Scottish waterfalls called the Grey Mare's Tail. I've been to about 6 Grey Mare's Tails in Scotland, I think. But you can see there's quite a nice path, runs up the side here and eventually goes up that loch at the top. So it's quite a good walk if you're able to do it on a nice sunny day. And as we've seen on the plate tectonic slide, the Earth's surface moves around slowly but constantly. Glasgow was on the equator about 300 million years ago, and it was a tropical swamp. We know this is true because the types of tree I showed you earlier in the Fossil Grove site could only grow in swamps. These swamps must have been huge and lasted for millions of years, since the Scottish lowlands have been a major source of coal, which, as you know, is just the fossilised remains of plants. Oop, gun there. Oh dear. Sorry, having another technical problem here. Right, sorry, I have to do this bit. Hey, this is called Glenroy. Oh, that's ruined my joke. I was touring up north looking for interesting things to see and dropped in on the Lochinver Geopark Visitor Centre to see if they could help me. I knew there's an interesting feature known as the parallel roads, but didn't have any geology books with me and no good internet connection at that time. I asked if they knew where they were so I could go and visit them. Sadly, they were unable to help me, so I had to give them a miss. Once I got home, I found out this was meant to be my joke. They were actually in Glenroy. It shares my name. In Gaelic, Glenroy actually means the Red Glen, and it's further south of Lochinver, down near Fort William. The following year, I did get there using the road from Roy Bridge. The parallel roads of Glenroy are loch terraces that formed along the shorelines of an ancient ice-dammed loch. The loch existed during a brief period, some 900 to 1100 years in duration, of climatic deterioration, during a much longer period of deglaciation, subsequent to the last main ice age. From a distance, they resemble man-made roads running along the side of the glen, hence the name. So again, hopefully you can see what looks like roads running along here. Charles Darwin visited the glen in June 1838 and concluded that the shorelines were raised beaches of marine origin. This was contradicted in 1840 by Agassiz's glacial theory, which stated that the Glenroy shoreline had actually been cut by a freeze-drop process during during the maximum extent of glacial ice in the climatic reversal known as the Loch Lomond Readvance. Darwin defended his paper over many years. However, after reading another paper by Charles Lyell in 1862, Darwin finally relented and said, "My paper is one long gigantic blunder." Here's another point of interest about Glenroy. Ice is heavy, very heavy. During the final stages of the last ice age, ground that had been ice-free in the north of the UK was again covered by major ice sheets. The weight of the ice made Britain into a seesaw, with the north being pushed down and the south lifting up. Obviously, this wasn't a very bouncy seesaw, so the East K is still subject to an isostatic rebound, as we call it in geology, in the north, with sinking in the south. Not good for the Thames Barrier. That's okay. I think the Thames Barrier will have crumbled to dust long before the uplift makes any difference to it. However, as I said, Glenroy keeps or helps understand this phenomenon, since there's a slight angle of difference between the levels of each road due to the increased pressure of nearby ice as they were formed. Most of what we've been looking at up until now has been of a very direct Scottish interest, but I'm now going to spend a short time talking about some huge geological events which are more global in extent. So there isn't too big a shock. We'll ease our way in by looking at some rock found in Islay. This rock's called a tillite. The way tillite is formed was first described by geologists working in Islay. It formed between 800 and 600 million years ago in shallow water when glaciers melted and dumped all the grit and rocks it picked up. This rock's almost a kilometre thick in Islay, so there must have been a huge number of glaciers forming them, then melting, forming, then melting, all at the same spot over millions of years. It was later confirmed that you'll find tillite of the same age at places all around the world. So how could that be? You've probably heard of snowball Earth. Just need to minimize this so you can read the slide. So one way of looking at it is according to this slide. Because there's an extended cold spell caused by something or another, oceans start freezing. So the polar caps start growing. And it says here on the slide, lowered reflectivity causes further cooling, but that doesn't make any sense to me. I mean, surely it's increased reflectivity. So there's more reflection of the sun, so the Earth cools down. That causes further cooling, ending in snowball Earth. Because there's ice over the whole Earth, CO2 can't get into the ocean anymore. However, CO2 outgassed by volcanoes builds up. That causes strong greenhouse effect, melting the snowball Earth, and then results in hothouse Earth, which again is another thing we know about. However, then the CO2 recycle restarts, pulls carbon dioxide back into the oceans, and it reduces greenhouse effect back to normal. So that's one way of looking at it. Although this slide shows the continents separately, some people think that snowball Earth happened at the time of the single continent, Rodinia. Today, the Gulf Stream carries warm water from the equatorial region and transports it to the North and South polar regions. We call this the North and South Atlantic Conveyor. And it's incredibly important since the current distributes nutrients throughout the ocean as well as distributing heat. This keeps them warmer than direct heating from the sun would and averages out global temperatures. Because the supercontinent of Rodinia was all at equatorial level, this meant there was no gap between the Americas and Europe to force circulation currents to exist. No warm water was forced to the polar regions, and that allowed the ice caps to slowly migrate northward and southward to the equator. This version of events suggests that once the supercontinent started to break up, volcanoes formed in the rift valleys, and the dark-coloured magma and dust from volcanoes covered the ice, which warmed and melted. This wouldn't have been one continuous event, but there would be many warmings and coolings and shifting of glaciers over hundreds of thousands of years. So this would explain the tilites on Isla, which we saw a few minutes ago, and the fact that they are everywhere else on the Earth. There's several other theories to describe how snowball Earth came about, but you just have to choose the one you like best. This is a 2.1 billion year old piece of banded ironstone, which I think looks absolutely stunning. But why is it banded? About 4 billion years ago, the first single-celled organisms came into being. Oxygen is a reducing agent and would have immediately destroyed any of these organisms. However, there wasn't any oxygen about at that point. However, about 3.5 billion years ago, some maritime organisms started to develop the ability to photosynthesize their energy requirements, giving off oxygen into the atmosphere in the process. The sea at this time contained vast amounts of dissolved iron, some of which would be deposited on the sea floor. Over time, as the amount of oxygen in the atmosphere increased, it began to be absorbed back into the oceans. And when it came into contact with ferrous iron, the iron rusted, turned red, and fell to the sea floor, building up a layer of red-coloured rock. However, once the oxygen levels became too high, it killed most of the organisms in the ocean that had produced it. And we had another period where no rusting took place, and the deposits that fell to the sea floor were black. This repeated time and time again for hundreds of millions of years. And one of the ways we know this had happened is by examining rocks like these. Banded iron formations like this account for more than 60% of the global iron reserves and can be found all over the world, notably in Australia, Brazil, Canada, Russia, and the United States. This is the Lyell salt mine in Sicily. This mine alone can produce 500,000 tons of salt per annum, and it's only one of hundreds of salt mines in the Mediterranean Sea. The salt layer is 40 meters thick and extends for miles. The question is, where did all this salt come from? The mine is located on Sicily, which is in the middle of the Mediterranean. The geology of Med is hugely complex, and I spent an enjoyable 60 hours at lectures exploring some of it in Glasgow Uni. But like most things geological, it's the way the area used to be rather than how it looks now, which tells the story. One favourite fact of mine is that large parts of Italy, including the whole of Sicily, are actually part of Africa as far as the geology is concerned, although it's part of Europe as the politicians would have you believe. Another interesting fact is that the amount of fresh water that runs into the Med from rivers and direct rainfall is less than the amount of water that evaporates from it. The only thing that stops it disappearing is water from the Atlantic pouring in through the Straits of Gibraltar. And that's a clue to where all the salt came from. We have good reason to believe that on several occasions, the Straits of Gibraltar were uplifted by the pressure of the African plate colliding with the Eurasian plate, causing a dam which stopped the Atlantic topping up the water level. It's also thought there might have been a hotspot underneath doing the same thing. Nobody's 100% sure. Over a few 100,000 years, around 5 million years ago, the sea dried up completely and huge amounts of salt air created the massive deposit you can see today. It then flooded again, got dammed again, flooded again, got dammed again, several times, each time building up the depth of the rock salt. Just to finish, swing back to Scotland to finish things off. The only meteorite impact to be discovered anywhere in Britain or Ireland lies beneath a large area of Scotland, centred on Lyell up in Sutherland. Clues to an ancient meteor impact have been found in the past, in terms of rock fragments altered by the tremendous heat and pressure generated by an impact event. However, the recent analysis has shown that the magnitude of the event and the probable impact site. Evidence of the giant ancient meteorite impact were identified near Allapool, west of Ross, in 2008 by geologists from Oxford and Aberdeen universities. These deposits of green molten rock, that's this stuff in here, mixed in with red sandstone, are almost 1.2 billion years old. The crater we saw a few seconds ago is at least 24 miles in diameter, and it's calculated that the impact released energy equivalent to 1,500 billion tons of TNT. So Scotland had its own Big Bang. So there you are. I hope I've been able to show you some interesting places to go and visit once we can move about more freely, or at least look at the Scottish landscape with a slightly different viewpoint. So if anybody wants to ask me any questions about the presentation, I'll do my best to try and answer it. Thank you.
Yes, just showing there, just north of Ullapool, there's a little peninsula above that. It looks over onto a Kiltybuie.
Yeah.
It's a nice walk out at the end. And I noticed years ago there that you're walking on sand with shells in it at about 800 meters above the sea. And, you know, that points out the lifting and the movement of the layers of rock. And the other thing, on Skye, Loch Ramsay, top end of Skye, there's a nice walk round the peninsula around the top there, and you can see some fossils of centipedes, massive centipedes. We're talking about 3 meters long, the feet of these centipedes. And when you go to the museum in Skye, they tell you that, you know, at the time these were wandering around on Skye, that was when it was more or less on the equator.
Yeah,
it's fascinating. Yeah.
Certainly, what I was trying to do in the presentation was keep things simple, but also be factual, which a bit of a balancing act. So the geologists amongst you probably thought it was a bit oversimplified, and those that don't know geology might have been a bit.
Spent a lot of time at Glenroy as well,
with the rock names
and the parallel roads, and it's brilliant around there. Thank you very much. Really enjoyed it.
Right.
Yeah, that was fascinating, Roy. Thank you very much.
Yeah, it was. It was really good. Yeah. It brought a lot of stuff back from, I remember that image where you had the picture with the thrust fault, the Moyne one, because I remember that from geology module with the OU.
Yeah,
I remember seeing that image, you know. And I agree with you, that banded iron, that was really something else. It was really nice looking, that.
When I go to geology lectures at Glasgow Uni, afterwards we normally go for tea, and you're in one of the main classrooms, and they've got a huge piece of banded ironstone there. So to see it in real life, it's absolutely gorgeous stuff. It's brilliant.
Aye. Oh, it looked really fantastic.
Yeah. Oh, somebody's phone's gone.
Sorry
I
about
know,
that.
It's okay.
I know it was mine earlier.
Oh, you go to.
Talking of phones, I can switch this off now because I don't need to see what's going on.
That's really good. I've been to Uluru and to the Olgas, and see the two connected was really good. Yeah.
Aye.
I didn't realise they were actually connected deep underground.
Which bit, sorry? Oh, the staff and
The Olgas and Uluru.
Oh, that one, sorry.
Yeah. Yeah.
Yeah. Well, every time, I mean, people have said to me, "Oh, why don't you go and see Air's rockets?" Incredible. It's this in the middle of
tell them.
There's just this
Tell
hill. It's not. There's hundreds of Stansford hills all around it. So it's a bit of a con. My wife was over in Australia and went to visit it, and it's one of the most expensive places in the world to go and see.
Oh, because it's miles from anywhere.
You know, they stay in a hotel, and you have to pay what it is for the hotel. And she was a bit unfortunate when she went out. It's the usual. They get you up at 5 o'clock in the morning. So you drive the 10 miles out to the viewpoint to watch the sun come up. And of course it was cloudy and the sun never came up.
That was right.
I'm terribly pleased about that either.
It was clear the day I went there, and they got us up at 3 in the morning that time. Because
did you not find it incredibly expensive?
We camped overnight.
Right. Okay.
So we didn't actually have a hotel. We just wanted to see it anyway. So.
When I was there, the timing was such that we had to see the sunrise and the sunset on the same day.
Oh, okay.
Oh, right.
That'd be nice. So a bit of journey back then, but something to eat and then back out again.
Yeah, it is quite a way out. So.
We were doing as much of Australia as we could in, I think it was 17 days. I saw about 2/3 of the continent. Very briefly.
Did well to get that in.
The old place.
It was a rather tight schedule. Arrive at 4 a.m., start a 12-hour sightseeing tour at 8 a.m. Wow.
Roy, I was going to say there was an interesting parallel with that talk about Airy, who was the Royal Society. I mean, same as Hutton, you couldn't help noticing they all seem to be sort of polymaths in these days, dabbling in nothing.
Yeah.
I mean, it really is interesting. They're able to bring all the knowledge of other subjects together and find so many things. It's fascinating.
I think you could sort of say on one level that there was less to know back then. You know, people didn't have to specialize for 6 years just to learn one thing. Because I mean, Hutton became a doctor, a medical doctor in 4 years as well. But having said that, the width of these guys' knowledge is phenomenal. You know, they all seem to know a lot of maths, and they were all erudite. They were all very literate. You know, the new, well, as you say,
polymaths. Going to university at 14. I mean, I think McLauden was professor of maths at Glasgow, but 15 or something. Yeah. It's incredible.
Aye.
Yeah. Really much to learn. I blame all the academics.
Yeah.
I mean, back then they didn't have TV, they didn't have like social media or anything. So therefore, they had just their books to read and that, you know. So that was how they learn all that information at such a young age and became really knowledgeable in a variety of subjects. Because I mean, they had nothing else to occupy their time, really.
Yeah.
So that's it. Get rid of Facebook and all the rest of it, and we got with an explosion of knowledge.
Mm.
I suppose any teacher who's found the pupils all playing on phones and so on would probably agree with that.
I mean, again, the wee story about Hutton was sort of, I was explaining, you know, he was part of Edinburgh Society. He was at the university there, and he would be involved in all sorts of subjects, but it was actually only because he got kicked out and had to go to the farm that he was then able to concentrate on one subject, and the subject was eventually, you know, well, he did maths as well. But, you know, geology then became an all-consuming interest because he wasn't able to look at anything else. So it's one of these wee quirks. Makes, like, you know, these stories quite interesting.
Same with that Mary Annan. I mean, she was just in the right place at the right time, I suppose, and finding all these, you know, that was her interest, you know.
Well, plus she did it for money. It was the only way she could get money. So had to, in all weather, risk her life at the bottom of the cliffs, find good stuff. So again, you know, we sort of look back on that. Oh, it's all very romantic. You know, you're in the Jurassic coast and you get to see all these wonderful things. But at the end of the day, probably if she didn't find stuff, she'd starve.
Because I mean, they didn't have. I mean, women back then, they didn't have like the same social standing as the men. You know, they weren't taken as seriously as the men.
It's tougher.
So, but these people, I mean, it's true what they say, you're standing on the shoulders of giants, you know, these people, because they've discovered so much that allows future generations to actually learn about and to actually see, whether it's in a museum or, you know, or go to the Jurassic Coast.
You have to say that Scotland and actually UK generally is an amazing place to do geology because there's so much mixture of it. Half the periods are named after places in the UK and Scotland, aren't they?
Well, again, that was sort of what I was trying to say. An awful lot of the early stuff did come out of Scotland, which is quite surprising for such a tiny place. So I went to Canada once. And they
I've just been looking at sorry, I beg your pardon. I've just been looking for it. I've got a book recently, my son bought me it, on a famous geologist, and he was building railways and canals. And it was because of that he realized about the strata in rocks and things. And he was, does anybody know his name?
Sorry,
I've got the books.
Who was that you said? Sorry, David, I missed the...
Yes, 19th century, and he was building canals and railways.
But who was? Sorry, who was?
I'm trying to think of his name, and I've got the book.
Hey, Telford, probably, isn't it?
I mean, he was very well known. I mean, there's a book about him, but I just can't bring his name to mind. I'm just looking there for the book, and I can't see it.
Well, Telford's the most famous canal builder. I mean, he certainly did quite a lot.
But his knowledge of geology came out. He noticed that, you know, 30 miles further on, there's the same strata in the rock and different height. And then he started, well, he made a map of the whole of the UK, I believe.
Right.
William Smith.
I'm a physicist, so I can't remember his name, but...
Wasn't William Smith, was it?
Yeah, yes, that's right. Smith was in it, yeah. But I can recommend the book. It's an excellent book. It describes how he's interested in.
Right.
I'm curious about how you measure the weight of a mountain with a pendulum. It sounds a bit kind of Heath Robinson. Anyone with a bit of string and a heavy weight could do it. But
have you been up Schiehallion?
I have been, yes.
Yeah, I have as well. And I mean, I taught physics for 30 years, and we measured G in the lab, you know, but very, very, very roughly. But yes, it did work. The deflection was a quarter of a degree or something like that, and it was done more than once. I know I've talked about it in the past, and I've got PowerPoints with it described in it somewhere. But but that was because that was from the point of physics, you know, I was interested.
Aye, fascinating.
Mhm.
And Schiehallion, you can see it every time you cross Ronancoa. You know, it's
Yeah.
sticks up there, triangular mountain.
Aye.
So is the principle then that the mass of the mountain just pulls the mass of the pendulum slightly towards it?
No, I mean, what you're talking about is the center of mass of the mountain. So, because it's a regularly shaped mountain, triangular almost, you can get an estimate of approximately where its center of mass is. And you've got the pendulum hung on the side of the mountain, a certain distance away from where you estimate the center of mass to be. So you've got the distance between the two. And the equation is the force acting to pull the pendulum to one side, it's a mutual force, and it's equal to a large constant, big G, times mass 1, which is the mass of the pendulum, mass 2, the mass of the mountain, divided by the distance between them squared. And doing that, and getting that very slight deflection, they came up with a value for G. The value of G is about something like 10 to the minus 6 newtons, or whatever units it is, you work it out with those. And it gave a reasonable estimate of the value of big G. And of course, it was big G that was used to show that all around the universe, the laws of physics apply as far as we can see. You know, that you use the same laws for things on the Earth, and attraction between you and the Earth and the Moon and the Earth. The Moon orbits around the Earth, and the force to keep it, centripetal force to keep it in orbit around the Earth, is calculated using this big G times M1, M2 over the distance squared.
Mhm.
Where the distance there is from the center of mass of the Earth to the center of mass of the Moon.
Been done a few times now.
Yeah.
I still haven't got many decimal places to it. It's really hard to work out.
Yeah. I used to know it when I was teaching, when it's actually 20 minutes. Yeah, it's to remember the value. It's something like 6.6 times 10 to the minus 6 units, if you work out the units. It's it'll be meters squared over kilograms squared or something like that.
I can't remember. I did that. I used that equation in quite a few OU modules during my first degree. So, because we used it in the astrophysics course. Aye, because we used it in the energetic universe course. You know, so it was constantly, that was one of the main equations really you had to use in quite a few of the tutor marked assignments.
Yeah, we're talking a gravitational constant then, are we? That used to be, well, in engineering we always use it 32.2 pounds per foot squared. That was it, or per foot per foot.
Right.
That's what I remember. But it's fascinating to be able to get it so accurate, isn't it? Amazing.
It's actually 0.673 times 10 to the minus 11 newtons per meter squared, kilogram square. I'm just looking it up now.
Aye, because I was going to look it up myself, David, because I couldn't remember it off the heart.
Very big. It's a very weak force, but the whole point is it's a very weak force, but I've lost my zoom now. It's a very weak force, but when you've got very massive objects, and then it's quite a large force. So you need quite a large force to keep the Moon orbiting the Earth. But when you look at it, the actual constant in that equation is 10 to the minus 11.
Aye.
Really tiny compared to the other forces.
Aye. Because I used to know I used to know them off by heart and that when I did the modules, but I haven't done the modules for years, so it fades out your brain. Unless you're using it a lot, It speeds out your brain.
Yeah. You can always look it up.
Actually, that's why I like physics, because you don't remember a whole lot of facts. And most physicists and scientists, engineers, they don't have to remember these equations, they just apply them. And that's why I preferred it much to biology and chemistry, where you had to remember an awful lot more.
Aye. I didn't like chemistry, and I were acquainted with one another, but we didn't like one another. That was my excuse, and I was sticking to it because I couldn't grasp it really. All the chemical equations, and we had to work out for some of them the modules I did with OU. Oh, it was a nightmare.
Chemistry's got a lot to do with geology as well, and you think of so many different kinds of rocks, and they've all got different chemical compositions. And what the question that comes to my mind is, there must be an awful lot of very different physical and chemical processes that ended up with all these different kinds of rocks all mixed up together, or different layers or whatever. I don't know how that came about.
Yeah, that's very true. I mean, I actually did physics and chemistry, so, but I've always taught physics because it's a cleaner subject to teach.
Physics is everything.
Kenny, you're still muted.
Yeah.
I mean, I used to know about what you're saying, Klaus, but it's gone from my brain now. I used to know all the information because we had to write about it in the tutor marked assignments, but now I'm on to psychology now, so.
Could you
wants to say something?
In layman's terms, why the black colons are black and the red colons are red?
You're asking me why there?
Yeah, why?
I don't know. I just did the presentation. Look it up.
Okay.
It's on Wikipedia. I'm assuming there's more gabbro in the black colons, but I don't know.
Well, yeah, I think so. But it's a process with which one take them out and require more gabbro than the other. And there must be something to do with their age and the way they were formed. Thanks.
Thank you very much for an excellent talk. Really enjoyed it. I'm hoping to set up some of these things myself. The only thing I'm not sure about is how do you put the PowerPoint on and have your own things? Well, is it easily explainable when you go into Zoom? Never tried.
Yeah, I mean, it comes up. There's a big button down at the bottom that says share screen. So
And
effectively,
can you
you
Zoom?
have PowerPoint sitting there as one of your windows.
Can you use Zoom extended so you can look at your notes?
What I do. I actually have my notes.
Oh, you're giving the game away now.
So Max just sits down underneath the screen. So if you thought I was looking down all the time, it's because I was looking down all the time.
Well, I use extended when I'm doing my talks.
Aye, Kenny, it's just what Roy said. I'm just on Wikipedia here because I did all this stuff when I did geology. The black colons, they're composed of gabbro.
Yep.
Whereas the red colons are mainly granite.
Yep.
So that's why the red colons are red and the black colons are black.
Okay. Does it give anything about ages or when they were formed? Because they're right next door to one another. So why is... Listen, Alison, thanks very much for that.
I have a look because there's it did tell you. There's quite a lot of information here. So if you go onto Wikipedia,
okay,
the cones, and it tells you about the black and the red cones. I mean, there is. I mean, it's millions of years ago, but I just I can't see. Do you know, Roy, when they were formed?
Not offhand. I never like quoting things because I'll get it wrong.
I see. I'm the same. Unless I know for certain that I've looked it up and that, you know, and then I can. Right, but I'm just having a quick scroll through. But you'd be just as well to have a read, and there'll probably be geology books that you can look up as well. As to, I mean, I've got quite a few geology books, but I don't know whether there's anything.
That's a good one. Mountain building in Scotland from the Open University.
All right, right.
Part of their
Which course was that?
Sorry?
Was that a particular course? Or?
Yeah, it was part of a level 3 course. I think it was one of the options.
Ah, right. Oh, okay. I gave up on geology before level 3.
I don't remember doing that. I did. I know when it was. I've done oceanography and I did geology and the geology one, second level geology one. Oceanography was the third level one I did. So.
I did the first level summer school at Heriot Watt, and we went out on a bus tour to the Scottish beaches to look at things.
All right.
Fascinating. Yeah.
Because my friend that I read to on a Sunday, Henry, he went to Durham when we did the geology course way back in 2000. He went there, and with the OU, but because Durham's like hilly and all that, it was steep. It was no good for a wheelchair user, and a lot of they took you on a bus, because Henry, my friend Henry, he videoed a lot of the stuff when they were going out and about. He just took a wee video and sent me the video, so it was like I was there, but I wasn't there, if you know what I mean.
Yeah.
So it was brilliant, you know, because he took pictures and he sent me some rock samples as well that he had picked up, you know, so it was really good. But because there was other geology ones, how the Earth works, the Earth's interior, and I mean there was various other geology ones that I did, and a lot of the summer schools or whatever, they were out in the middle of nowhere, you know, out in a field, and you were traipsing to like a beach and that, which is not good for. And they said, oh, you could go, but you'd just be stuck in the place, you know, on your own. And I'm like, well, what's the point in that? I'd rather just be at home rather than stuck in a big science room, you know, the geology science room with nobody there.
Yeah.
But that was really good.
Anyway, yeah. Anyway, can I say thank you very much, Roy, because I have to be aware that was an excellent talk.
All right.
I enjoyed it. Thank you very much.
Yeah, very good indeed, Roy.
It was.
Look forward to the next one, in fact. Okay, anyway, I must leave just now. Bye for now.
I've also got to go, so thank you very much.
Bye.
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 Thank you all. Bye.
Bye.
Thank you, Roy. That was wonderful.
Yes.
Thank you.
Yes. Thanks very much.
Thanks, Roy.
Yeah.
We'll see you in a fortnight.
Let's give Roy.
Right. Thank you, Roy. See you in a fortnight.
Yeah.